Good morning, everybody. I hope everybody's doing well. I am completely, well, I don't know what I was going to say there, actually. I was going to say I'm completely ready for class today, but you guys already know that. All right. So today we're going through 10.3 and stepping into 10.4, which is the last section we do in this course. So welcome to it. We're at the very end. Kind of nice. 10.3 is only 2 pages of lecture notes. And actually, it's just a single theorem and a single example because most of 10.3 in the textbook is a review of polars and, polar equations, polar curves, that type of thing. In our MyOpenMath website, I have in the, I'm going to double check before I say this. In the section corresponding to 10.3 in the MyOpenMath website, there are 2 prerequisite videos. If you need a review of the polar coordinate system for calculus, I put one of my videos there. And then there's also a review of the area of a sector, which is actually for the next section, but whatever. I put both review videos right there. So those should help you if you can't remember much about polar coordinate system. Those should fill in those gaps. Really quickly, I'm just going to mention kind of the biggies, the big important part about polars here. So polar coordinate system is when you have, maybe I should back up. The Cartesian coordinate system, as you recall, is a set of ordered pairs, right? You go over X units left or right, Y units up or down. That's the Etch-a-Sketch type of movement. So everything is grid based, right? It's your whole world is just this hash of grids. You go over 1, 2 units and up 1, 2 units, and you arrive at something. Okay, that is the Cartesian coordinate system, what we're completely used to. And maybe I should write that in a Cartesian coordinate. But the polar coordinate system, if you've never been, Amsterdam is set up sort of like a polar coordinate system, where you have a radius and an angle, which we'll refer to as theta. That's how you list the ordered pairs in the polar coordinate system. So that's a polar coordinate. And if you look at the polar coordinate system, technically there isn't even a y-axis, actually. There's just a pole, which is a point in space, which we would call the origin normally. And you would have what we would call the polar axis. And then to get to any point in space, you would step out so many units and turn through an angle. Now, that's actually not how I teach it. I teach it that you first, because you're always standing at the pole initially, you first turn through an angle. So let's say that you want to turn through an angle of 3 pi over 4. Let's just pretend 3 pi over 4. That's what the, geez, my ink is really bad today. That's what the angle is that you just turn through. And then let's say you want to step out 2 units. So if that's 2 units and you turn through an angle of 3 pi over 4, that point would be called 2 comma 3 pi over 4. Also, again, if you're standing at the pole and you turn through an angle of 3 pi over 4, but you step back 2 units, then you have landed at the point negative 2 comma 3 pi over 4. Unlike the Cartesian coordinate system, there are an infinite number of representations of points in the polar coordinate system. In the Cartesian coordinate system, the point 1, 1, there's only one way to get there. 1, 1, that's it. But the polar coordinate system, to get to, let's say, 2 comma 3 pi over 4, you could go to 2 comma 3 pi over 4, or you can go to 2 comma 3 pi over 4 plus 2 pi. Or you can go to 2 comma 3 pi over 4 plus 2 pi k, where k is an integer. So there's an infinite number of representations to get to that point. Also, you could have technically turned through an angle of negative pi over 4. That would be this angle right here. and stepped backwards 2 units. So again, another kind of grouping of or different ways to mention or to arrive at that same point. So just as a quick reminder, those are polar coordinates. The x value, there's a relationship to convert between polar coordinates and Cartesian coordinates, and there's a way to convert between Cartesian coordinates and polar coordinates. The one that we're going to concern ourselves with here is to convert from polars to Cartesians. That is, we're going to write down the definition of x and y in terms of their polar coordinates. So this is not the proof. I'm just using the space. Actually, I'll just use it off to the right here. I'll say where x is going to be r cosine of theta. Y is going to be r sine of theta. This is actually born of the unit circle. So when you think about the unit circle right here, if you have a point on it, the point is actually, well, we would call it xy, but the x value for a point on the unit circle is actually defined to be the cosine of theta, the angle you've turned through, and the y value is the sine of theta. Sorry, that looks like a 0. It's supposed to be theta. My ink's too thick today there. If you go beyond a unit circle, then you're dealing with, let's get a really nice, that's not what I wanted. Let's get actually a nice circle in here. If you go beyond the size of a unit circle, so let's say that we have a circle of radius, I don't care what this radius is, let's just pretend it's a circle of radius 5. Okay. So if this were a circle of radius 5, oops, that was supposed to be a 5, but for some reason it came out as an R in my brain, all right? Then a point on that circle of radius 5 is no longer the cosine of theta, sine of theta. Instead, it's actually the radius times cosine of theta and the radius times sine of theta. And you can kind of see that just by using right triangle trig. If this angle's theta and this hypotenuse is of length r, then you could easily find out just from your old school trig that that point is r cosine of theta and the y value is the r sine of theta. So that's where all of polar coordinate systems is actually derived from, is a circle of radius r. So that's wonderful. Now, all that being laid down, that's the theory I just needed to kind of throw down very quickly because I just want to get into this proof here. Let's mention how you would take the derivative of a function if given to you in polar coordinates. So if I give you a polar equation, all right, so given some polar equation r, which is actually a function of an angle theta. That's what a polar equation is. Actually, we say it right here, but I'm going to just call r is equal to r of theta. Okay, so if you're given that r is a function of theta, well, we know that x is r cosine of theta and y is r sine of theta, always. Where r is, again, a function of theta. Then the derivative of y with respect to x. In other words, what we want to do is we want to find out what's the slope of the tangent line at some point, all right? Well, we know from not Cartesians, but from parametrics, because that's all that a polar coordinate system is parametrics, right? If I wrote it this way, x is equal to r, I have to zoom in, otherwise my ink goes wacky. If I wrote it this way, x is equal to r cosine of theta and y is equal to r sine of theta. I hope you realize that's actually a parametric equation. Parametric curve. X is defined to be something in terms of t, and y is defined to be something in terms of t. However, I'm going to scoot things over slightly because technically r is also a function of time. And I say time, but really it's theta, but time and theta, whatever. It's just a variable. So that is a parametric curve. So we know from our previous work that if you want to find the derivative of y with respect to x, you would divide both numerator and denominator by d theta, dy d theta over dx d theta, and you do some magic. So dy dx is equal to, we were writing as dy dt last two classes. Now we're going to write it as dy d theta because that's the variable over dx d theta. And then we're going to go ahead and look at y here, and we're going to take the derivative of that function with respect to theta. That is a product of two functions of theta, and so we need to use the product rule. Drinking my chai, sorry about that. So let's go ahead and use the product rule on that. I'll go down the line. So if y is equal to r of theta sine of theta, then dy d theta is derivative of r with respect to theta times the sine of theta plus r times the derivative with respect to theta of the sine of theta. Now, I know I could have just written the cosine of theta there, but I'm just taking my time to showcase the mindset of the derivative of that numerator. Same thing in the denominator. The denominator is dx d theta, and we know that x is r of theta cosine of theta. So let's go ahead and use the product rule there. We'll take the derivative of the first, dr d theta, times the second, plus the first times the derivative of the second. Cleaning this up, we get r prime, which that's how I'm going to write it, is just r prime. It's just easier. R prime sine of theta plus r cos of theta divided by r prime cos of theta minus, because the derivative of the cosine is negative, r sine of theta. And we have actually proven a theorem. This is exactly what this theorem is saying. The derivative of y with respect to x is going to be dr d theta sine of theta plus r cosine of theta divided by dr d theta cosine of theta minus r sine of theta. Now, when I was a student, I found that memorizing this formula was pretty daunting. We are at the end of the course. Your brain is full of other things. So here's what I recommend that you do. Just remember, x is always equal to r cosine of theta, y is equal to r sine of theta, and take those derivatives. Just remember that r is a function and cosine is a function and sine is a function. So when you take those derivatives, they're product rules. But you can rebuild this derivative every single time if you need to. If you're like me and you don't like to memorize, which is a good and a bad thing at times. If you don't like to memorize, that means you have to be pretty solid with your theory. However, people who do memorize can be faster than you. That's just how life goes. That's just how it is. All right. So again, what we have mentioned in the past is that horizontal tangents occur when your numerator on your derivative is 0, but we also require the denominator is not identically 0. Okay. And along the same lines, if you want to find vertical tangents, well, those occur when the denominator is 0, but the numerator is not. That's the only thing we're learning in this section. The rest of the section in the textbook is a review of polar coordinates. If you look at the homework for this section, I think there's 4 problems and they all revolve around derivatives. So good luck with that, right? Not too bad. Let's go ahead and just do an example. Determine the equation of the tangent line to this polar curve at theta equals pi over 6 when the tangent lines are horizontal. I don't know why there's a question mark there. let me erase my question mark. That's a silly way of, there we go. Little artwork. There we go. Determine the equation of the tangent line to that polar curve at, oh, I get it. When are the tangent lines horizontal? No, it wasn't when it's when are. Sorry, yeah, the question mark does actually apply there. All right, so I'm really covering all the bases here. I'm having us take a derivative, and I'm also having us take a look at when are those tangent lines actually horizontal. Now, I'm going to do something first that I expect you already have experience with, but probably don't remember how to do. What I'm about to do is prerequisite to the course, but again, completely forgivable if you have not seen it in a year and it's brand new to, or it's going to seem newish to you. I'm going to graph this polar curve. So really quickly, I'm going to change it, first of all, to a Cartesian coordinate curve. I'm going to say, let's go ahead and graph. Now, this is not actually part of the problem, but I just want you to see where I'd like you to be at. Graph y is equal to 8 sine of x plus 3. Notice all I did was just replace theta with x and r with y. There's this very specific reason. This is how I generally graph polar curves. I first graph them in their Cartesian form, and then I translate them over to polar coordinates. You will not have to actually do this, so don't freak out. But in Calc 3, it is a good idea to know how to quickly graph some of these curves. So I'm just going to go ahead and represent kind of the skill set you'd like to have in Calc 3. And you can always just bookmark my review on polar coordinate system video. And then as you get closer to Calc 3, you can go ahead and rewatch that as many times as you need to. So what I do is I draw in the midline at y equals 3, because that's a sine function lifted up 3 units. So here's my midline at y equals 3. I'm going to leave that out. Y is equal to 3. I know it's a regular old sine function, not negative sine, but a regular old sine. So I'll go ahead and graph a regular old sine. Just one cycle is all that's needed. Notice, by the way, the argument of this sine is just 1x. In other words, it hasn't been stretched or compressed horizontally. So this, and it also hasn't been moved left or right. So this is x equals 0. That's x equals 2 pi. The midpoint right there is pi. Here's pi over 2. This should all be really kind of stuff that you guys are pretty awesome with at this point. And then I see that the way I've graphed this, I'm going to do one little thing here. The way that I've graphed this is not going to be fair to when I go to graph, because the amplitude of my sine curve is actually 8. So I'm going to kind of amplify this up a little bit. That's actually not bad for freehanding that. Okay, and so then I'm going to draw in my x and y axes. Really, I don't need the y, but the x is very important. I'll draw in the y first, though, just to showcase it. I'll use blue for my axes here. There we go. Something I need to mention here, since the amplitude is 8, I know that this is 3 plus 8 up here, which is 11. And since, again, the amplitude of my sine curve is 8, this is 3 minus 8, or a negative 5. And finally, I'm going to draw in the x-axis, which is somewhere between 3 and negative 5. That's more like right here, probably. All right. All that being done, said and done, I'm going to use that to graph my polar curve. You may have never graphed a polar curve this way. And the only polar curves you should be required to know how to graph are curves of the form r is equal to a plus or minus b sine or cosine of theta, or r is equal to a sine or cosine of theta. There are other ones like r is equal to a sine of b theta. Those are multi-petal roses, and they are somewhat important, but generally I'm okay with my students just being able to go to Desmos very quickly to graph that out to see what they look like. But these ones you should be able to graph by hand. And so notice that's the kind I'm graphing here. Okay. Now, what I'm going to do is I am going to play a little game. The game I'm playing is that I'm standing on the x-axis. Let me go ahead and just throw myself on the x-axis somewhere. Let's see, what color am I not using? Red. So I'm standing here on the x-axis at time 0. And I'm going to start throwing rocks. And you may say, what the heck does he mean by throwing rocks? Well, the rocks I'm going to throw are the distances away from where I'm standing. Wherever the rock lands, it's so many units away from where I'm standing. And that's going to tell me something about how I'm going to graph my polar curve. My polar curve I'll graph down here. There's the pole, and there's a by hand polar axis. I'm going to start at x equals 0, which corresponds to the angle of 0. So when I'm facing an angle of 0, or in other words, when I'm standing at x equals 0, I'm throwing a rock 3 feet in front of me. 1, 2, 3. Then as I turn through other angles, I'm throwing rocks farther and farther out in front of me until I'm finally facing an angle of pi over 2 where I throw a rock 11 feet in front of me. So as I turn, I'm throwing rocks further and further and further away until I turn and I'm facing the angle of pi over 2. That's the furthest away that I throw a rock. Notice what I've done here with all these dots is I've actually carved out a path of travel for all of these rocks that I'm throwing out in front of me as I turn. All right. Then I continue to turn past an angle of pi over 2, and I'm still throwing rocks way in front of me, but they're not as far as 11 feet in front of me. In fact, by the time I'm facing an angle of pi, they're only 3 feet in front of me. So by the time I'm facing this direction right here, I will have thrown a rock 3 feet in front of me. But as I was turning, I was throwing rocks less. The distances were getting smaller and smaller. So something like this. You can see that's like if I face that direction, I'm throwing a rock over here. If I face this direction, I'm throwing a rock further out, right? This direction, I was throwing a rock there. So here's the path of travel for the rocks that I've thrown. Erase all that. Now I'm going to go beyond the angle of pi. I'm going to start turning to quadrant 3, basically. As I turn past pi, all of a sudden the rocks, they are less than 3 feet in front of me, right? So I'm just a little bit past pi. Maybe this is 2 feet in front of me. This might be 1 feet in front of me. Then this is at my feet. So very quickly after I turn through an angle of pi, facing this direction, maybe then facing this direction, the rocks get really close to me. So by the time I'm facing maybe just slightly past pi, I've dropped a rock at my feet. So again, the path of travel looks like this. But then what happens after I get to that very special angle when I drop a rock at my feet? Well, as I continue to turn past that very special angle, all of a sudden, I'm throwing rocks below the x-axis, which means behind me, until I face an angle of 3 pi over 2. That is, as I turn past this angle right here and continue to turn and continue to turn and continue to turn and continue to turn, I'm throwing rocks behind me until I'm facing an angle of 3 pi over 2, where I'm throwing a rock 5 feet behind me. Maybe I should make that more like 5 feet. Something like that. If you guys know your old polars, this is called a limison with an inner loop. And then I continue turning past 3 pi over 2, throwing rocks behind me until I get to a very special angle before I'm facing 2 pi, where I drop a rock at my feet. This is symmetric, so actually it just does this. In fact, the rest of the graph is symmetric, so you could technically just round it out like that. Okay, that's how I teach graphing polars in my trig class and then in my pre-calculus class. So, excuse me, that would be the graph of our polar curve. Now, obviously, you can hop over to Desmos and check that. I'm not going to. I'm just going to trust my graphing skills here. All right. So, determine the equation of tangent line to this when we're facing an angle of pi over 6. Here's the angle of pi over 6. So I want to know what's the equation of this tangent line right here. Well, let's go ahead and find out. We'll need to find the equation of a tangent line. You need a point and a slope. Write that down. Tangent lines require a point and a slope. I'll just do it that way. Let's go ahead and find the point first, since that's mechanically just algebra. At theta equals pi over 6, x of pi over 6, comma, y of pi over 6. Remember, x is r of theta, cosine of theta. Y is r of theta, sine of theta. Luckily, these are both special angles, so we are able to calculate cosine of pi over 6 and sine of pi over 6 very easily. I didn't really leave myself room, so I'm going to rope that up and scoot that over a little bit. Let's see. Actually, I'll just go ahead and take care of the cosines and sines there. So this is going to equal r of pi over 6 times root 3 over 2 and r of pi over 6 times 1/2. Now we go to r, and we see that r is equal to 3 plus 8 sine of theta. So r of pi over 6 would equal 3 plus 8 times 1/2. Not 8.5, but 8 times 1/2. So that'll be 4 plus 3, or 7. Let's go ahead and plug that in. 7 root 3 over 2 and 7/2. Notice that that point, x comma y, 7 root 3 over 2 and 7/2, is in quadrant 1 if you're working in the Cartesian coordinate system. And by the way, if looking at this as being the pole right here, this point on the curve at pi over 6 is definitely in quadrant 1. So there we go. That kind of matches our intuition, at least. 7 root 3 over 2 comma 7/2 is the point in Cartesians, not in polars. In polars, the point is, let's see, pi over 6. So 7 comma pi over 6 is what it would be in polars. But anyhow, so we have the x and y coordinate. Now we need the slope. Well, the slope is equal to the derivative of y with respect to x, but we're going to evaluate this at theta equals pi over 6. That notation there with the pipe means you're going to evaluate that at that specific value. Now, let's pretend for a moment that you've completely forgotten what the derivative of y with respect to x looks like for a polar equation. You could super quickly derive it. So dy d theta over dx d theta. I happen to know that y is r sine of theta and x is r cos of theta. So I know, just using the product rule, derivative of y with respect to theta is r prime sine plus r times the cosine. Now I should not use my shorthand there. Sorry about that. I'm very habituated to using shorthand. So And in the denominator, again, derivative of x with respect to theta, that would be r prime cosine of theta, and then minus r sine of theta because the derivative of the cosine is negative. So if you ever forget that formula, you could derive it that quickly. I want to evaluate that at pi over 6. Remember, r of pi over 6, you could just go right back up to the original r and plug in pi over 6, you will get 7. R prime, on the other hand, we did not compute. So let's go ahead and find out what R prime is. Looking back up at the R we started with, which was 3 plus 8 sine of theta, its derivative is 8 cosine of theta, which implies R prime of pi over 6 is going to be 8 root 3 over 2, or in other words, 4 root 3. Sorry, that prime is kind of wacky. And what are the other things we're going to need? Sines and cosines of pi over 6. Well, we already know what those are, but I'm going to write those here anyway, just so that you can see where I get all my numbers. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. And we're ready to go. No calculator needed. So this derivative, which is a slope, evaluated at pi over 6 is going to be r prime at pi over 6, which we just said was 4 root 3. Sine of pi over 6 plus r at pi over 6, which is 7. Cosine of pi over 6, root 3 over 2, all over r prime at pi over 6, cosine at pi over 6, minus r at pi over 6, sine at pi over 6. You can see there's a lot of little cleanup here. I'm going to multiply numerator and denominator by 2 because, well, it cleans up nicely when you do that. 4 root 3 plus 7 root 3 all over 12. Yeah, minus 7. And that will be 11 root 3 over 5. And let me just double check that I didn't screw anything up, but I don't think I did actually. 4 times 3 is 12. Yep. 7, 5. Yep. So there's our slope. So we have a slope and we have a point. So the equation of the tangent line at pi over 6 should be, write it here, y minus the y value that we just computed way up to the right there, which was 7/2, is equal to the slope over x minus the corresponding x value, which was 7 root 3 over 2. And honestly, there's not much cleanup that can happen here, I don't think. Let's see, y minus 7/2, just doing some algebra now, is 11 root 3 over 5x. Let's see, minus 77 times 3, whatever that is, 77. I'm just going to do it this way. There we go, 231. 231 over 10. Yeah. And then I would add 7/2 to both sides. So let's see. I get negative 196. Okay, so therefore y is equal to 11 root 3 over 5x minus 196 over 10. However, 196 is divisible by 2, so I might as well clean that up. That's 98/5. There's the equation of the tangent line to that curve at the angle pi over 6. Now, you could use Desmos to check this. I'm not going to bother, but you totally graph that polar curve in Desmos. If you go to Desmos and do that, by the way, type in r equals 3 plus 8 sine of, and then type in the word theta, Theta, and it will graph that polar curve. Just graph it from 0 to pi over or 0 to 2 pi. And then in the next line, you would graph y equals 11 root 3 over 5x minus 98 fifths. And you'll see that that is the tangent. Wait, I do have an issue with that. Notice how I immediately went, wait, hold on. Because if you look at that tangent line right there, its slope should be negative. Where did I do? There's 6. Oh, no. It's because I'm drawing this by hand. I will actually share. I'll go to Desmos and we'll graph it. It's because I'm graphing this by hand, and it is easy to convince yourself that you've graphed it correctly. But I sort of didn't mention that this bows out slightly. This curve will bow out slightly when it comes around. So really, this is the actual. It's when you're graphing by hand, you don't normally graph that bowing out business, but it does bow out slightly. I just want to share my screen and we'll graph that very quickly. Nothing big. I'm glad that I kind of figured that out quickly. So first of all, what I'm going to do is I'm going to go to a polar coordinate graph just so you can see the polar coordinate system there. And I'll do reverse contrast, take off the grid too. Oh, no, I like the grid in this case. All right. And our polar function was r is equal to, what did I say, 3 plus 8 sine. There we go. And you can see that actually does match, although I used red, so I'm going to change this to red. Why not, right? As well, they don't have a red, so I'll go purple. All right, so there's our polar curve. Notice it does bow out. It looks close to what we graphed. It's just, it bows out. I often don't have mine bow out that far. And then what we found for our tangent line was y is equal to 11 square root of 3 divided by 5x, and then minus 98 over 5. And looky, you can see it right here, that this is probably about an angle of pi over 6. If I graph, I don't think you can graph a polar point here. So I'm going to graph its corresponding Cartesian point, which was 7 root 3 over 2, comma 7 halves. There we go. So you can see that's the point on the curve right there. It does exist on our polar curve, and that is the tangent line to the polar curve at that point. Perfect. Yay. Now, the other part of this question was, when are the tangent lines horizontal? Now, in this case, it's very easy to see just from this graph or from our by hand graph that the tangent lines are going to be horizontal at the angle of pi over 2 and 3 pi over 2. However, let's not do it via the graph. Instead, let's do this analytically. Let's do this by hand is what that means. So let me go back to my screen here. While I do that, I'm going to take a sip of my chai. Un momento, por favor. All right. So we're back here. And the question is, when are the tangent lines horizontal? Well, those tangent lines are horizontal when this denominator here is 0, but the numerator here for the derivative is not. So I'm going to write that down below, right here maybe. Horizontal tangents occur when r prime sine theta plus r cos theta over r prime cos theta minus r sine theta. occur when this, and I'll point, is 0. But this cannot also be 0. Okay. There we go. All right, so let's go ahead and do that. Let's set the denominator equal to 0 here. Now, the denominator was r prime cosine of theta minus r sine of theta. R prime is 8 cosine of theta. R, on the other hand, is 3 plus 8 sine of theta. So you do have to kind of remember that R is a function, and you have to steal that function value. And you want this to be 0. Let's go ahead and clean things up. That'll be 8 cosine squared of theta minus 3 sine of theta. Let's see, minus 8 sine squared of theta is equal to 0. And back in trig, my trig students and my pre-cal students just reviewed all this. Solving trig equations, incredibly important. So here I'd like to get everything in terms of sines. Luckily, I know that cosine squared can be written as 1 minus the sine squared. I should really double check as I go through this to make sure I'm not distributing something broken or something like that, but I think I'm pretty good. Now, distributing through, I get 8 minus 8 sine squared minus another 8 sine squared will be a minus 16 sine squared minus 3 sine of theta. Now, I don't like to deal with quadratics with negative lead coefficients, so I'm going to go ahead and multiply everything by -1. So I get 16 sine squared of theta plus 3 sine of theta, and then minus 8 is equal to 0. And this is going to be, geez. Let's see. I'll write it this way, sine of theta. Sine of theta, oops, equals 0. Hopefully this factors nicely. I know that, say a plus or minus 1 would be nice, but it's not going to work out that way. Sorry, I'm just looking, but what I'm seeing here is I'm not going to get a nice clean solution to this as I'm going through. And why not? Oh, haha. I see why not. There's other places where we have horizontal tangents right here. We have 4 places where we have horizontal tangents. I'm like, why am I not getting that? Yeah. We have 4 places where we will have horizontal tangents. So let's go ahead. This I'm going to use quadratic formula for, actually. So I'm going to write this as 16. Let's not use sine here. Let's just keep it easy. We'll call it 16 u squared, because I did a u sub, plus 3u minus 8 is equal to 0. That means that u is equal to -3 plus or minus square root of 3 squared minus 4ac all over 2a. So you can see you're going to need a calculator for this. 32 and 16, that's 512, I think, but I'm just going to double check. 32 times 16. Oh, it is 512. You can take the square root of that, actually. All over 32. You cannot take the square root of that. Sorry. That's 2 to the 9th is what it would be. So I'm going to do this as 2 to the 8th times 2 so that I can take its square root. -3 plus or minus 2 to the 4th is 16 root 2 over 32. And that's as good as it gets. So what we're going to do here is you take the sine inverse. Oh, sorry. By the way, u was equal to sine of theta. So that will imply we will get a decimal approximation here because it's just going to have to. Implies that your reference angles, not your actual angles, but your reference angles are sine inverse of the, I always use absolute values here, absolute value of -3 plus 16 root 2 over 32. And the other reference angle, I'll call that reference angle 1 and reference angle 2. The other reference angle will be the sine inverse of the absolute value of -3 minus 16 root 2 over 32. I tend to, when I use inverse trig functions, I tend to only do them with their absolute values of their ratios that they're equal to. It's just safer to do that. I'm going to do this in radian mode. So let me just switch over to radian mode here. And let me clear my screen because I don't need that. And I'm going to do the sine inverse on my calculator. Sorry, that's kind of at this point just listening to me mumble about this. But see, -3 plus 16. Oops, delete 16 root 2. And that, and the numerator, and divide that by 32. So this one right here is approximately 0.66 radians. And the other one, darn it. Oh yeah, I can't do it, I think. Good. Let's see. Absolute value, so I want to make that a plus here maybe, is a 0.93. Roughly, again, radians. Both of those are quadrant 1 angles. Yeah. All right. So those are my reference angles. And then, dag nabbit. You know what I just found? Vertical tangents occur when your denominator is 0. Yeah. So I've just found, I'm wondering why. I was like, wow, that's weird that I'm not getting my pi over 2 and my 3 pi over 2. I'm finding vertical tangents. Darg nargit. That's why this problem was not supposed to be this complex. I apologize. Look at that. Not a big deal because we've done most of the lion's share of that, but I would like to actually do the easier one because that's the only kind I would ever ask. And let's go ahead and just finish this out with a vertical tangents because those I'm sorry. Well, let's do the horizontal tangents, the real horizontal tangents, where the numerator of our derivative is 0. For some reason, my brain just went to the denominator. Oddness. So I'm going to just, how do I want to do this? I'll do it like this. Yeah, just like that for vertical tangents. But the horizontal tangents are actually a lot easier in this case. The horizontal tangents, let that numerator be 0, r prime sine theta plus r cosine of theta, r prime being 8 cosine of theta, sine of theta, plus r cosine of theta, r being 3 plus 8 sine theta, and then we're going to multiply that by the sine of theta. Or by the cos of theta, sorry. And we want to set that equal to 0. This one actually is tons easier. If you take a look at this, you'll get, let's see, 8 cosine of theta, sine of theta. I'll leave it like that for right now. Plus 3 cosine of theta. And then plus another 8 cosine of theta, sine theta. So there'll be 16 of these altogether. And you can see that this is a ton easier. Factor out a cosine. And you'll be left with 16 sine of theta plus 3. So we see that this is 0 when cosine of theta is equal to 0, or when sine of theta is equal to a negative 3 over 16. Let me just double check that real quickly. R prime is 8 cos times sine plus 3 plus 8 sine times the cos. Yep. And now you can solve this out. And you know that cosine of theta is 0 at theta equals pi over 2 and 3 pi over 2, which is exactly, see how quickly that's what it was meant to be. Here's the pi over 2. And here's the 3 pi over 2. And then these other two right here correspond to theta being the sine inverse. Well, technically it's the reference angle. Theta hat is the sine inverse of positive 3/16, whatever that may be. I'll just do that very quickly. Sine inverse of 3 over 16. I get 0.19 roughly radians. And just to let you know, by the time we turned into this is a quadrant 3 angle. That's a quadrant 4 angle. So I have this reference angle for quadrant 3 and quadrant 4. That means that theta in quadrant 3 is pi plus that. And theta in quadrant 4 is 2 pi minus that reference angle. Those are all the spots where you have horizontal tangents. Much easier than what I had just gone through for the verticals. So sorry about that. Anyhow, that's how you do that style of problem. By screwing it up at first and then going back through and doing all horizontal tangents correctly. Horizontal tangents took 5 minutes. That wasn't too bad. All right, but the main thing I want you to get used to is just a derivative formula here. This bad boy right there. It is just going to be very useful for you. It's the last derivative formula you have to deal with. And then now we step into the final section